Hello dear viewers. Today we are going to learn modular arithmetic and Chinese remainder theorem. So let's start with the very basic. So let's start with the division. Let's take an example that I'm going to divide 10 with a 7. Then 7 ones are 7 and remainder is 3. So now basically the modulus means the remainder. Like if I'm going to write 10 mod 7, so that is congruent to 3. So remainder is 3, or you can write equal to 3. So the congruency, we will discuss that later. So now here 3 is our remainder, and this is 7 is the divisor. This is quotient. This is dividend. So here we are concerned about the remainder. So this was very simple. So as this 10 is a positive number, so it's very easy that you make a simple division, and whatever the remainder is, that is the answer of modulus. Now let's learn that how to find the modulus of a negative number. How to find that? You can use the simple division method. Put minus 10 over here, 7 is over here. Now you can see here what we have. We have a 7 over here. So now this 7 should always be less than the current dividend. So here if I will write 7 into minus 1, that is minus 7, but minus 7 is greater than minus 10, so it should be smaller. So that's why here we are going to use 2. So 7 2s are 14, it should be 14. Okay, changing the sign. Okay, so now we are having a 4. So now minus 10 mod 7, that is equal to 4. Okay, so this is pretty easy. So now let's consider the third case. The third case is if we are going to find 10 inverse modulus 7, and that is congruent to 1 by 10 mod 7. So now here we are having two methods. The first one is Navy method or brute force method. Fine. Okay, let's see this first. So in this Navy method, what we are going to do, we are going to write 10 mod 7, that is equal to x mod 7. Okay, so now x, that is always less than 7, so that's why x mod 7. Now 1 mod 7, that is equal to 10x mod 7. So now you are going to fill this x from x that varies from 1 to wherever, whenever you will get an answer. So now let's take x is equal to 1, then that would be 10, x is equal to 2, then 20, x is equal to 3, 30, x is equal to 4, 40, 5, 50, 6, 60, and so on. So now you are going to check this, that 10x mod 7 will give you the remainder 1. So that's, in this way you are going to find the x. For x, that is equal to 7, 10, and if you divide 10 with the 7, you are having a remainder 3. Here you are having the 7 to the 14, 6, and here 28 and remainder is 2. Here 7, okay, 5. 7 5 is 35, 5 is remainder, 7 7s are 14 and 1 is remainder. So here 1 is the remainder. So this is our answer. Here should be a 50, and whenever x is 5, then we are having a 50. So it means 1 by 10 mod 7 that is equal to 5 mod 7, or that is congruent to 5 mod 7. So here you can write that is equal to 5. So 10 inverse mod 7 that is equal to 5. So now there is another method, that is extended Euler's algorithm. Extended Euler's algorithm. So what this algorithm says, so let's have a look. Ax that is congruent to Ax that is congruent to 1 mod m. Okay, so if this will true if A and B are co-prime. So co-primes means GCD of A and B that is equal to 1, or you can say HCF of ABC is equal to 1. Okay, so now that implies AX plus BY that is equal to GCD of A comma B. So now here this is actually the Euler's algorithm or equation. So here A and B, AX and BY that is equal to GCD of A and B. So we are considering A and B. But if A and B are co-prime, then this condition always holds. Okay. So now you can further elaborate that thing. AX plus BY that is 1 mod m. You can take this equation. So I hope you understand this. So that equation is derived from this. If GCD of A and B is equal to 1, then AX that is 1 mod m. Okay. So now okay. AX plus BY that is equal to GCD of A comma B. Now let's consider GCD of A comma B that is equal to 1, means A and B are co-prime. So now we are going to take a modulus of a B on both sides in this equation. So AX mod B plus BY mod B that is equal to GCD of AB that is equal to 1 mod B. So now as y is multiple of a B, if it's a multiple of B, then its remainder would be 0. So this whole term would be 0 in our case. So now we are left with AX mod B that is equal to 1. So we are going to use this equation for finding the inverse. So let's see that how we are going to do that. So the basic idea is that using this one remainder and going back to the top in a reverse order. So now let's see that how we are going to implement that thing. So now first we are having two values, 10 and 7. So taking the bigger value on the left hand side. Now that is equal to ax plus b5 GCD of a and b. So now we are going to make a factor with respect to 7. 7 into 1 plus 3. So now we have used 7 and 3 to make a 10. So similarly we are now using these two values, greater one over here. 7 is equal to 3 into 2 plus 1. So now here we are having a 1. It means our 7 and 10 are co-prime. So that's why we will have a 1, the minimum value, that is 1. 1 is a GCD of 7 and 10. So now here we can use this equation. We can rewrite it 1 equal to 7 minus 3 into 2. Now remember, we are not going to solve this equation over here. We are going to make this equation in form of 10 and 7, the multiples of 7 and 10. To make this like this, a, b, find multiple, this x and y would be the multiple of that. So we are exploiting this GCD of AB. Now in this case 7 and 10 are co-prime, so that's why we are having a GCD 1 and backtracking to the original form. So now here we are having a 3. We are going to put the value for 3 from this above equation. So now value for 3, 1 equal to 7 minus, so value of 3 would be 10 minus 7 into 1. 10 minus, I can write 7 into 1, now this into 2. So further 7 minus, okay, so first we are going to multiply that thing, 2 into 10 minus 7 into 2. 1, that is equal to 7 minus, okay, 2 into 10, okay, so that would be plus 7 into 2. So taking these two 7s and combining that thing, if we take a 7 common from here, so we are having a 1 plus 2. So that would be 3 into 7 minus 2 into 10. So we are having our equation in the multiple of 7 and 10. So this is like, this is form ax plus by, that is equal to GCD of AB. So that is equal to that. So now the further step is taking the mod. So we are going to take a mod of 7 from the both sides, that is 1 mod 7, that is equal to, again this is a multiple of a 7 as we already discussed in that extended Euclidean algorithm. So the mod 7 would give me 0, so we are having a, this is minus 2 into 10 mod 7. So 10 is the multiplication over here, that would be 1 by 10 mod 7, that is equal to minus 2 mod 7. So minus 2 mod 7 is very easy to calculate. Minus 2, 7, okay, minus 1, that would be minus 7. So here that would be a plus sign, plus 7 minus 2, 5. So we are having a 5 over here. So here you can check that you already calculate with a Navy algorithm. So now one more theorem we are going to discuss, that is Fermat little theorem. Fermat's little theorem. It says that a raised to power p minus 1 mod p, that is always congruent to 1 mod p or equal to 1. So let's take an example. It's very easy when you are going to find the modulus of very large number. So let's take any random number. and the 11 would be the prime number. So if we are having a equation in this form, some number a, this is a, raised to power 10 mod 11. So that is always give you a 1 according to the Fermat's little theorem. So this was the basic of your modular arithmetic. So in next video lecture we are going to use this all modulus arithmetic to solve the Chinese remainder theorem. So if you are having any doubt, any problem, you can ask in a description box. Thanks for watching. Thank you.